Good afternoon. My name is Adam Sullivan. I'm the acting state engineer and the principal administrator of the Nevada Division of Water Resources. And I will be kicking off this panel today on the State Water Resource Initiative. This is a proposal that's a collaborative effort between the state and the USGS Nevada Water Science Center and the Desert Research Institute to update groundwater budget calculations across Nevada. These water budgets are the foundation for determining perennial yield and groundwater availability statewide. So this is a project that is something that the state needs for our office to enhance our capability for comprehensive management of Nevada's water resources into the future. The first stages of the initiative are the subject of today's panel discussion. Specifically, we'll be describing some of the types of information and methods of analysis that are currently available for calculating groundwater discharge, recharge, and regional groundwater budgets, and the effort required to update these calculations on a statewide basis. We'll also be discussing some of the history of how these data were initially developed as part of USGS water resource bulletins and reconnaissance series many decades ago, and some of the limitations largely recognized by the authors at the time of the use of these data for determining water availability. Water right appropriations are established in part on a determination of whether there is water available at the source of supply. The state's primary guideline for determining groundwater availability within a basin is the perennial yield, which is defined as the maximum amount of groundwater that can be developed each year over the long term without depleting the source. So the primary reference for water budget information used to establish perennial yield has historically been USGS studies that are now between 50 and 60 and are increasingly being challenged. Where there's an increased demand for water, more recent studies have often been completed by various authors to recalculate water budgets and revise perennial yield. As our office is charged with considering the best available science in making decisions, these new studies have been adopted at times where they were regarded to be a more accurate determination of the water budget. But this has generally been done in a reactive manner where there were protested applications. And what we want to do here is really get ahead of that and improve the science before there's a dispute. Perennial yield has commonly been estimated as the entire groundwater flow budget fluxing through a particular area. And this has been the standard going back to the 1940s when they were seeking some quantitative measure of groundwater availability. The state engineer had very little data to work with to be responsive to the demand for groundwater for irrigation at that time. For instance, for desert land entries that were flooding into concentrated localized areas. So between the 1940s and the 1970s, groundwater budgets were calculated at a basin scale across most of the state, generally based on estimates of regional groundwater discharge or recharge, and then perennial yield was estimated from that and used by the state engineer as a guideline for groundwater availability. Now, through today's lens, there are many shortcomings or criticisms of this, starting with, well, if you appropriate all of the groundwater up to the entire discharge, then eventually you're going to dry up springs, reduce base flow, affect groundwater-dependent ecosystems, and that's not right. But it's also far from being that simple. The amount of groundwater available may depend on a variety of other variables, like the location and the depth of a well, the structural heterogeneity within a basin, aquifer parameters, water quality, and on a larger scale, the water budget, it might be a minuscule fraction of the total volume of water in storage, so that development of the perennial yield would have a negligible or non-measurable impact on surface features over thousands of years, because the water that's being developed is coming out of storage rather than being captured from discharge. So these are all examples of complexities that make perennial yield an oversimplified measure of groundwater available to appropriate. Nevertheless, perennial yield is an important guideline to understand the ultimate limits of a water budget, and our state agency really needs this kind of a guideline to do our job and to be responsive in water rights administration in a reasonable time frame. To be most effective into the future, we need to recognize and account for the complexities in determining water availability and perennial yield. But this really begins with an improved baseline understanding of water budgets that are up to date, scientifically sound, and non-biased. So in recent years, many significant scientific advancements have been made that allow for us to do that, and that's what the subject of this panel is today. The first two stages of this initiative would update baseline groundwater budget calculations across the state. And this is the component that as a state agency we're seeking funding to complete. This will then provide a sound scientific basis to address later stages, which are focused more on how to determine groundwater availability for appropriation. These are maybe more complex questions and certainly require a substantial component of public outreach and working with water users and local communities to communicate the science and consider the context and the reasonable planning horizons, and then the impacts of having this updated science available. So we'll discuss this more at the end of the panel, but at this point I'd like to turn it over to the USGS as our next panelist.
Thank you, Adam. My name is Kip Allender. I'm a hydrologist with the USGS Nevada Water Science Center, and the co-author and co-panelist that helped with this session was Phil Gardner, also a hydrologist with the Nevada Water Science Center. So what we want to do in this segment of the panel session is to provide some historical perspective for the context of the Nevada State Water Initiative, and in particular talk about Nevada's early groundwater program that occurred through the Reconnaissance and Water Resource Bulletin Series investigations from the mid-1940s through the 1960s, and in particular talk about some of the methods and approaches that were used during that time and the limitations associated with that work. So this slide shows the timeline for the early water resource investigations in the state of Nevada. It was 1938 that the Congress appropriated funding for the USGS to cooperate with state agencies across the nation to investigate and better understand the availability of water resources throughout their states. And so this is when it began within the state of Nevada as well. And then it was 1944 that systematic investigations of water resources began in the state, and it began in Las Vegas Valley as they were experiencing a decline in flowing wells and the artesian pressures that region had enjoyed for a period of time. And then in 1946, this became formalized within the Water Resource Bulletin Series, which is that red report shown up in the upper right. And that went for 15 years plus, and then in 1960 was the beginning of the Groundwater Resource Reconnaissance Series, which was initiated really to help fill in the gaps from the Bulletin Series to try to better understand where other development opportunities existed across the state where groundwater information was limited. The Bulletin Series and the Reconnaissance Series were referred to as the Nevada Groundwater Program at the time. All the Bulletin Series as well as the Reconnaissance Series reports are available from the Division of Water Resources website. So what was the initial motivation for the Nevada Groundwater Program? Really, it was a combination of two major factors, and that was the availability of cheap hydroelectric power from Hoover Dam that became available to the state of Nevada in the mid-1940s, as well as the advent of the electric turbine pump, which really changed the ability to use groundwater for agricultural purposes. So with the availability of cheap energy and the advent of the new pumping technology, this really made for an opportunity to develop Nevada's groundwater resources for agricultural purposes. Because by this time, all the streams and all the surface water across the state had been appropriated. So this really was going to allow the state an economic opportunity to develop additional resources. So the state of Nevada and the USGS realized that this was an opportunity to do an assessment of the availability of the water resources, as well as to look at the depths to groundwater, because that was important for the cost of lifting water. Was one of the major constraints, and this would allow farmers and ranchers to invest in locations around the state with less risk. The other benefit of conducting the water resource investigations at the time was the state was thinking ahead and thinking about conservation and not over allocating the groundwater resources, and they wanted to try to contain the overdevelopment of the resource. Was that from the early Nevada groundwater program, the state engineer realized that there was a need for coordination amongst the various water resource agencies, or the agencies that were conducting various water resource activities in the state, and so he convened a meeting in 1946 to discuss what everybody was up to with regard to Nevada's water resources, and then it was mostly involving state and federal agencies, and everyone at the meeting decided that it was a really good idea to continue to have these meetings year after year, and so it was established as an annual meeting thereafter, and that of course evolved into the Nevada Water Resources Association. So the early water resource investigations really primarily focused on estimating water budgets for the hydrographic areas, and in particular focusing on discharge and recharge. Discharge, of course, was the easiest thing to measure because it was more readily observable and quantifiable, and the approach the early investigators used was to go into these valleys, into these hydrographic areas, to drive around or to go to a high point and to identify where the zones are, where the phreatophytic vegetation or in the areas of groundwater discharge were occurring from, and to coarsely map those areas, and then to assign real general ET rates that were just more or less a real broad guess based on some estimates that had been made in other states, as well as a few real early preliminary tank studies. Really only applied one or two rates to the entire groundwater discharge areas. They took that rate, multiplied it times the area, and came up with a discharge volume, called that the groundwater discharge. For a recharge, in the closed basins, they would just, knowing that the systems were in dynamic equilibrium, they would just assume that the recharge was equal to the discharge, and they just call them equivalent. But later, after a few investigations, Tom Eakin and George Maxey realized that some basins were kind of out of balance with respect to groundwater recharge and discharge, and started realizing that these systems were a little bit more complex, and that there was interbasin flow occurring. And so they developed a method which became the Maxey-Eakin method in 1949, and then that method was used extensively to independently estimate recharge, and that's what I'll talk about next. The Maxey-Eakin method for estimating recharge in the state of Nevada was first introduced in Water Resources Bulletin number 8. Essentially, the method calculates or estimates recharge as a percent of annual precipitation for specified precipitation zones within a hydrographic area. It was developed by balancing recharge and discharge from 13 east central Nevada valleys, by optimizing the coefficient to multiply times the precipitation times the area. Now, the Maxey-Eakin recharge estimates were never intended to be the final estimates. According to Tom Eakin, the method was developed mainly as a reconnaissance tool to provide a rapid and consistent means of assessing water availability for estimating the potential power requirements. Additionally, Tom Eakin felt that the method that they had developed was a conservative estimate and that future detailed and controlled investigations would probably result in values that were at least as much as the initial estimate, with the hopes that the final recharge would be higher than their initial estimates. The Maxey-Eakin method for estimating recharge was developed over 70 years ago, yet it remains one of the most widely used methods to estimate groundwater recharge in the Great Basin, as well as in surrounding states and in other areas. But as a result, the recharge estimates and water budgets that are based on the Maxey-Eakin method are increasingly challenged over time. This has big impact on Nevada's water resources, and in particular on the conceptualization of many of our multi-basin groundwater flow systems, which have in part been derived from the Maxey-Eakin based recharge estimates. So historic interbasin flow estimates between hydrographic areas in the state of Nevada were derived in part from the imbalance between discharge and the Maxey-Eakin recharge, as well as from hydraulic head data, which was very minimal at the time during the Bulletin Series and Reconnaissance Series days. The interbasin flow estimates are really highly sensitive to the uncertainty in the water budget and can have a big impact on the magnitude of the estimates. And this has a big effect on the defining and understanding the regional flow systems, as they were the original basis for recognizing and defining our regional flow systems. For example, the interbasin flow estimate between Spring Valley and Snake Valley in eastern Nevada, which is shown in this map on the right, has undergone much investigation and has varied substantially over time. The original estimate in 1965 by Rush and Kazmi was around 4,000 acre-feet per year, which was a very conservative estimate at the time. And as time went on, there was lots more estimates that went all the way up to 33,000 acre-feet per year, which is what was shown here from the Barkas study, and then has since been revised back downwards on numerous occasions. And then the most recent estimate was around 8,000 acre-feet per year by David Prudick in 2015. So the early estimates of water budgets and interbasin flow were the basis for the conceptualization of many of our regional flow systems. However, with the uncertainty of a lot of the water budgets and some of the interbasin flow estimates, this means that some of that conceptualization could be refined or revised with a better understanding of these numbers. And this is important for the state because the flow systems have started becoming more important for the management of our groundwater resources. For example, in the White River flow system, it was recently decided that it would be managed as the entire flow system would be managed rather than by individual hydrographic areas. And so this could become a future development for other basin or flow systems as well. And so it's important to have as good an understanding as we can of these interbasin flows and water budgets, as well as any refinements that we might need to our basin, to the conceptualization of our flow systems. So that concludes this section on the historic perspective of the Nevada groundwater program, and it's leading now to Justin Huntington, who's going to talk about some of the new technologies and approaches that have developed in the last 50 to 70 years that weren't available to the early developers of the water resource estimates across the state, and for which there's new opportunities. So with that, take it away, Justin.
Hi, my name is Justin Huntington. I'm a research professor of hydrology at the Desert Research Institute. And I'm going to provide an overview of new technologies and opportunities we have to support the new State Water Resources Initiative. So we've come a long way in Earth observations with the start of the Landsat program in 1971. Landsat 5 was launched in 1984 and, by the way, holds the Guinness World Record of the longest operating Earth observation satellite at 29 years long. We now have many imaging platforms, including Landsat, Sentinel, Planet, MODIS, and many others. And now we can combine these newly available satellite data with new in situ observations and gridded weather data, such as SNOWTEL, PRISM, DayMet, GridMet, and many others, which is really necessary to provide insight into drivers of change, whether they be natural or due to water and land management or other factors. And to deal with all these data sets, now we have cloud computing, cloud data catalogs, and application programming interfaces, or APIs, really paving the way for natural resource scientists to focus more on the science rather than endlessly wrangling data and trying to make the data work together. And now that we have nearly 100 years of new precipitation data and new precipitation distributions developed with those data sets, it's important for us to understand how these new distributions differ from old ones. First off, the Hardman precipitation map was capped at greater than 20 inches. This resulted in the Hardman map substantially underpredicting precipitation in areas with high elevation or in high elevation, as can be seen from these figures, where Hardman precipitation is on the left, PRISM is in the middle, and the percent difference between PRISM minus Hardman is on the right, where orange and red indicate PRISM is greater than Hardman at the basin scale. In some areas, PRISM is 50 to 100% greater than the Hardman precipitation map. PRISM is based on long-term observations of precipitation from the National Weather Service, SNOWTEL, Remote Automated Weather Stations or ROS stations, and USGS and Nevada Division of Water Resources High Elevation Precipitation Gauge Network datasets. However, assessing the accuracy of PRISM and other precipitation maps remains a challenge given there are few independent observations to compare to quote-unquote measurements of precipitation. These measurements of precipitation often have large errors due to undercatch, unshielded gauges, non-heated tipping buckets, and poor storage gauge maintenance, such as installing screens and removing them to keep the bugs out. Comparing multiple precipitation maps against each other, understanding what control points or observations were used, and obtaining independent, high-quality observations in study areas of interest is really needed to provide insight into accuracy and uncertainty of different precipitation maps such as PRISM, DayMet, GridMet, and others. With respect to recharge using empirical models, new max-econ type of approaches have been developed over the years using new discharge estimates such as Nichols 2000 and the bootstrap brute force method of Epstein and others. However, concerns on the accuracy of those discharge estimates in which recharge coefficients were calibrated to remain. Also, issues and concerns related to the transferability and regional application of max-econ type of approaches remain. Development and application of precipitation and mountain block water yield and runoff relationships, such as those developed for the Carson and Virginia Range by Maurer and others, Berger and Huntington, have been useful for estimating mountain front recharge, where water yield minus runoff equals recharge. However, a few independent estimates of recharge exist, such as those derived from Darcy flux and chloride mass balance estimates, and this type of approach is limited in application to regions with similar mountain block geology, vegetation, and climate in which the functions were developed. With respect to recharge using water balance models, many new physically based water balance models such as the Precipitation Runoff Modeling System or PRMS and the Basin Characterization Model or BCM, forced with spatially distributed precipitation and evaporative demand, really offer new potentials to estimate mountain block ET, runoff, and ultimately net infiltration. However, significant challenges in estimating the spatial distribution and magnitude of recharge with water balances models remained. For example, mountain block and streambed hydraulic properties are often ignored in simulating diffuse mountain block recharge and focused recharge from runoff across alluvial fans. Better understanding and accounting for mountain block geology and runoff transmission losses across alluvial fans is really needed for improving water balance model estimates of recharge. This requires more knowledge and incorporation of hydrogeologic information within hydrologic models. In basins that are terminal or where subsurface discharge is thought to be minimal, recharge estimates can be assessed and potentially calibrated to using independent discharge estimates. So let's talk about groundwater discharge. As John Bredehoeft said in this guest editorial in the Journal of Groundwater, it is the discharge. He highlights that generally the recharge is the most difficult component of the groundwater system to quantify, and that while research to better understand the recharge may be useful, it is more fruitful to examine the discharge. The discharge is there to be observed. It occurs as springs, as base flow to streams, as bare soil evaporation and transpiration from phreatophytes. He opines that, quote, there is a reason why hydrogeologists in Nevada still use the Maxey-Egan method to estimate recharge, a method published in 1949. No one has come up with an improved procedure to estimate recharge, even given 50+ years of further investigation. On the other hand, the methods of measuring phreatophyte discharge are greatly improved. He concludes by saying, I have no doubt that studying recharge will be high on the list of research topics for the future. I'm also confident that the recharge is better understood through the discharge, where there is an integrated and observable hydrologic signal, and that discharge is much more pragmatic concern than recharge. It is these opinions and facts that has led our group to focus on groundwater evapotranspiration from phreatophytes using newly available satellite images of surface temperature, vegetation vigor, along with gridded weather data of solar radiation, temperature, humidity, and wind speed. So in 2009, the USGS opened up the Landsat archive for free. Prior to this, Landsat images cost anywhere between $600 to thousands of dollars per image, which is really why Landsat data wasn't heavily relied on in past groundwater discharge studies. Just for Nevada, it would have cost $15 million for the archive alone. Now it's freely available via USGS, Google, and Amazon clouds. With all this new information, we've been able to refine phreatophyte boundaries using Landsat, new high spatial and temporal resolution imagery such as from the Planet SmallSat constellation, combined with groundwater levels, digital terrain, aerial imagery such as from the National Agricultural Imagery Program, or NAIP, and fieldwork to identify and map indicator species such as greasewood, saltgrass, saccaton, and willows. The map on the right shows a comparison of different delineations of potential areas of groundwater discharge for Caraco Lake Valley in the Humboldt River Basin, where delineations from older studies, as expected, were quite general, and as studies incorporated more and more information, delineations become more detailed, and in this basin, reduce in aerial extent. The animation in the middle is based on Planet 3-meter resolution satellite imagery, and it illustrates just how dynamic phreatophyte vegetation vigor is for the Johnson Spring Complex. With new satellite imagery and climate data sets, many new and exciting opportunities exist to better understand phreatophyte vegetation distributions, dynamics, and sensitivity to climate and water and land management. Over the last 20 years, numerous advancements have been made in estimating groundwater evapotranspiration from phreatophyte vegetation, really beginning with the great work of Randy Lasniak and Dave Nichols at the USGS Nevada Water Science Center, and studies focused in the Death Valley and Eastern Nevada regions. These advancements typically consist of pairing in situ micrometeorological station-based estimates of ET with plant cover percentages, or a combination of vegetation indices and climate information such as reference ET or potential ET and precipitation. New work that normalizes empirical relationships between ET and vegetation indices by including climate drivers of ET allow for transferability of functions while considering the primary drivers of ET in the basin of interest. It's important to acknowledge that considerable uncertainty in groundwater ET estimates exists, especially in areas of low phreatophyte vegetation cover. This uncertainty can be characterized statistically based on confidence and prediction intervals around regressions, and also by collecting additional in situ station-based estimates of groundwater ET. Such efforts will ultimately help to better understand and to quantify uncertainty in estimated groundwater ET across the state. Here's an example application of the Beamer approach over the Humboldt River Basin using the Landsat archive combined with respective GridMap potential ET and precipitation data. Notice how spatially variable vegetation cover is and how estimates of groundwater ET honor that spatial variability. Maps like this are being generated each year starting in 1985 and are ultimately being used to estimate long-term medium estimates of groundwater ET rates and volumes for each basin to support groundwater modeling studies. With respect to agricultural water use, updates to evapotranspiration and irrigation water requirement estimates were made in 2010 using physically based estimates of reference ET based on the Pima-Monteith equation and National Weather Service measurements of temperature and precipitation with estimates of solar radiation, humidity, and wind speed. In the past, simple temperature-only equations were used to estimate reference ET and irrigation water requirements as part of the Nevada Irrigation Guide. Now we have physically based equations, daily soil water balance models, and new gridded weather and climate data sets consisting of solar radiation, temperature, humidity, and wind speed, along with over a decade of in situ weather station measurements over irrigated agriculture to compare and ultimately bias correct spatially distributed reference ET estimates. Having accurate, spatially distributed estimates of reference ET is important since Nevada has the least number of National Weather Service and agricultural weather stations in the country, and no climate or weather information exists in many basins where significant irrigation occurs. Measuring climate and weather over agricultural regions is important since it is quite different from adjacent dry lands where it is cooler, more humid, and typically less windy in agricultural regions due to the evaporative cooling effect. The Nevada Integrated Climate and Evapotranspiration Network, or NICENet, consists of 18 weather stations located in agricultural fields across the state that records high-quality measurements of solar radiation, temperature, humidity, and wind speed, along with precipitation, to better reflect agricultural conditions when estimating irrigation water requirements. However, NICENet is currently unfunded. Over 70% of permitted water rights are for irrigation. Also, the majority of groundwater discharge occurs as pumping and subsequent consumptive use by crops. Therefore, developing accurate estimates of consumptive water use from irrigated agriculture is important for developing and updating groundwater budgets. In addition, given the lack of historical metered pumping data, estimates of consumptive water use serve as the basis for estimating historical pumping. And while metering all groundwater pumping would provide much needed information on pumped and applied water, meter ratings do not equate to consumptive use of applied water, which is the amount of applied water lost to the atmosphere. Ultimately, it is the consumptive use that is needed for updating groundwater budgets, developing groundwater models, and for long-term groundwater management. Now, with readily available satellite-based ET estimates and metered pumping data in selected basins, statistical relationships between pumping and ET can be developed and then applied to estimate pumping for periods and areas with no pumping information. To do so, actual places of use must be delineated and paired to permitted or water right places of use, and requires identifying and developing one-to-many and many-to-one relationships where meters can serve more than one field, and one field can be tied to multiple meters. Clearly, there's a need to develop a consistent approach that is based on best available science to estimate statewide historical pumping using a combination of historical meter data, actual and permitted water right places of use, crop inventories, irrigation type, and satellite-based ET estimates. So speaking of satellite-based ET estimates, I wanted to highlight a project called OpenET that we can leverage for the State Water Resources Initiative. OpenET uses publicly available data from multiple satellites, weather stations, and gridded weather data sets, along with the Google Earth Engine cloud computing platform to bring together several models for calculating ET over large areas at the field scale for the very first time. The OpenET project has brought together the scientific community behind different ET approaches, including those of the USGS, USDA, NASA, and several university partners, to make consistent field-scale estimates of ET based on best available science, and has developed a user interface and application programming interface, or API, to make the data easily accessible for users to view and to download. In Nevada, ET estimates are summarized over actual places of use that were digitized based on multiple data sets used to define historical agricultural areas over time and estimate the maximum irrigation extent that include changes in irrigation practice and field shapes, such as the conversion from wheel line to center pivot irrigation. Data sets used to define historical irrigation extents include Landsat satellite NDVI data from 1985 to 2019, NAPE imagery from 2017, and place of use boundary data sets from the Nevada Division of Water Resources, along with Common Land Unit boundary data sets, or CLU data, derived from the USDA Farm Service Agency. These field boundaries are ultimately attributed with monthly actual ET derived from satellite data, reference ET derived from GridMet, precipitation from GridMet, area, and annual irrigation status of cultivated, non-cultivated, rain-fed, wetland for each year from 1985 to current, derived using a machine learning model. Illustrated is a screenshot of the OpenET Data Explorer platform where a user can zoom in to an area of interest, view the raster ET data, view the field averaged ET data for the year of interest, select a field of interest, and view the monthly ET, total ET for the year, crop type, area, and also cumulative ET for the last 4 years through the Data Explorer page. OpenET data will really be useful for estimating historical and current consumptive use across the state and will ultimately help to inform groundwater budgets, modeling, and management efforts. Public launch of OpenET is planned for later this year. If you'd like to know more about the Nevada actual place of use field boundaries, see Jaden Atkins' undergraduate poster, Development of an Agricultural Field Boundary GIS Dataset for Consumptive Use Mapping in Nevada. And I'm giving a presentation on OpenET on Wednesday, the 27th at 2 p.m. As part of the State Water Resources Initiative, it'll be really important to assess the accuracy of satellite-based ET estimates, not only for irrigated agriculture, but also for phreatified areas. This will involve collecting in-situ ET data and performing detailed accuracy assessments in areas where uncertainty and water budget sensitivity to changes in ET may be high. So in reflecting on the importance of quantifying ET and groundwater discharge for the State Water Resources Initiative, we really shouldn't lose focus on the importance of accurately estimating recharge. Daniel Stevens published a commentary on just that, and in response to John Bredehoff's editorial, it is the discharge. He notes that some groundwater basins may have no superficial expression of discharge at all, and in these cases, one may need to calculate discharge using Darcy's law. To do this requires assessing subsurface geologic structure and stratigraphy, determining the width and saturated thickness of the aquifer, installing wells for establishing the hydraulic gradient, and conducting aquifer tests. Although this standard hydrogeologic information should be collected as part of an evaluation, the uncertainty in computing discharge this way can be considerable, especially where there may be flow through multiple heterogeneous or fractured bedrock formations. Moreover, in deep basins, the cost of exploration and testing could be substantial. He points out that even if the discharge is of greatest pragmatic importance, one should consider the recharge methods to bolster the calculated discharge. And he argues that the spatial distribution of the recharge rate is a key requirement in numerical models of groundwater systems. The total basin discharge per se tells us little about this flux and its spatial distribution. So as the title of the commentary, we should also consider the recharge. On that point, and in thinking about how to better understand the recharge and its distribution, I want to talk briefly about integrated surface and groundwater models. These models can be used to evaluate the effects of such factors as land use change, climate variability, and groundwater withdrawals on surface and subsurface flow for watersheds that range from a few square kilometers to several thousand square kilometers, and for time periods that range from months to several decades. These models overcome many of the limitations of simplified approaches. However, they are complex and time-consuming to construct and parameterize, yet they provide detailed information on how recharge varies in space and time. This illustration shows an integrated surface and groundwater modeling result of seasonal recharge using a USGS integrated model called GSFlow, where it can be seen that during winter, little recharge occurs. During spring, most of the recharge occurs at low elevations and is concentrated within the alluvium as snowmelt occurs. And as springtime progresses into early summer, most of the recharge occurs at higher elevations within the alluvium, not the bedrock. This is all to say that just because there's more precipitation or snowmelt and less potentially T at high elevations doesn't necessarily mean there's more recharge, as most water balance and empirical models would suggest, and that the distribution of recharge will depend on the geology. For example, in carbonate mountain blocks, recharge could very well be highest at high elevations. Again, highlighting why it is important that we consider geology when estimating recharge and its spatial distribution. Now I'll turn it over to Kip Allender from the USGS Nevada Water Science Center to talk more about hydrologic models and potential uses for this initiative.
Okay, thank you, Justin. So now what I want to contribute to this discussion about the new technologies is a little bit more discussion about hydrologic models. Hydrologic models are very powerful tools for managing water resources, and that's because it gives our water managers a tool to make forecasts on what can happen to the hydrologic conditions as a result of management decisions. And these are decisions like whether to increase groundwater development or to appropriate additional water rights, and what those impacts are, what kind of interference those decisions might have on other users as well as on streams and or springs. It also can be used to understand how changes in the patterns or quantities of surface water use are going to impact the surface water system as well as other parts of the hydrologic system. And then also, as many folks are aware, it's a tool that's really badly needed to be able to adequately and successfully conjunctively manage groundwater and surface water as a single resource. Another place where groundwater models can really be useful for management is understanding, change of use or manner of use applications, water permits. And then, of course, understanding what kind of impacts climate change can have on the water resources and availability of water. This figure on the right is an example of an application of the Walker River model in Mason Valley, developed by the Desert Research Institute for understanding the impacts or potential impacts of curtailment on groundwater pumping irrigation wells, supplemental irrigation wells during periods of drought. So it's important to understand what hydrologic models bring for us and do for are based on, and what they do is they allow us to incorporate the sound principles of the way groundwater moves through a system, which is shown in the groundwater flow equation here, as well as to take into account the very complex interactions that can occur from various boundaries, and the example I show here is the various streams that are interacting with the groundwater system, as well as to understand and to represent very spatially variable properties within a system that are going to have a big impact in the way that the groundwater and surface water interact, or the way that groundwater moves in a system. And this map shows the spatial variability of transmissivity for the Death Valley Regional Flow System that was developed by Keith Alford and Tracy Jackson last year. The hydrologic models really take advantage of the many advances that Justin was talking about earlier, and in particular with the ability for the computation power of modern computers allow us to really dig deeper into these hydrologic problems. Advances in the numerical methods and the mathematics to solve that groundwater flow equation. The ability to distribute the computations to many computers, call that distributive computing, which is what we do with the capture maps. And the ability to more adequately estimate the parameters or the properties of the system, to be more realistic, to help us, based on the actual data that's available, and then to represent heterogeneity in a system, which before computers and models, you really had to simplify the properties in order to be able to solve the problems. And I just want to point out that we've made large advances in the last couple of years, really thanks to the work by Keith Halford, who really helped to pioneer and to push us in the direction of representing heterogeneity in systems and to honoring our hydraulic data, our hydrologic data, and not to let the geologic frameworks over dictate our understanding, because we learned that the hydrogeology is very important to understanding a system and to conceptualizing a framework, but it can trick us and fool us when hydrologic data actually tells us otherwise. So now we want to provide a broad overview and vision of the Nevada State Water Initiative, which is basically to use new technology and approaches to update the science of Nevada's water resources. And this program, the vision of this program is to re-estimate discharge and recharge, use that information to update water budgets, where interbasin flow estimates are poorly constrained or not well understood, to refine those estimates, and then to use all this information to refine our understandings of the regional flow systems, and then eventually to incorporate all this information into developing hydrologic models for the purpose of making forecasts for management questions and decision making.
The central task of the State Water Initiative will be to revise estimates of groundwater discharge from phreatophytes using best available science. This will involve delineating riparian and non-riparian potential areas of groundwater ET and developing revised estimates of groundwater ET based on field investigations, in situ ET estimates, groundwater levels, GIS, and gridded climate and satellite data sets. In addition, collection of new in situ micrometeorological station-based estimates of groundwater ET is proposed in areas of extensive sparse phreatophyte vegetation cover and other areas where relatively large uncertainties in groundwater ET exists. An example of proposed efforts is shown here in the Humboldt River Basin, where numerous field investigations were conducted, riparian and non-riparian phreatophyte areas were delineated, and groundwater ET estimates were revised and compared to previous estimates using over 30 years of gridded climate and satellite-derived vegetation indices. An important part of the State Water Resources Initiative will be to refine and develop estimates of historical pumping. This will include collecting, organizing, developing, and summarizing meter data, crop inventories, power records, point of diversion locations, actual and permitted places of use, and new satellite-based ET estimates across the state. These efforts will be extensive, but much needed in order to develop a statewide historic pumping data set that is consistent in time and across different basins and is based on best available science. New historical pumping estimates developed from this initiative will ultimately serve as a primary source of information in revising groundwater budgets across the state, support special studies, and support groundwater management activities into the future.
The vision for re-estimating recharge under the State Water Initiative is to move away from the Maxey-Aiken approach used historically and to move towards more modern approaches and methods such as what Justin was discussing earlier, to use water balance methods and models for estimating recharge, to use gridded weather data which distributes precipitation much more realistically, as as well as thoroughly across the state. And also to honor the things that we know that affect the recharge process, such as drainage. Water tends to collect in drainages, and drainages is where focused recharge often occurs. As well as geology, we know that carbonate rocks tend to be a much better receptor for recharge than clastic rocks, for example. Also, incorporating our understanding of soils and soil distribution. Some soils drain much better than other soils, where some soils will reject water, and use that information to refine our estimates for the magnitude of recharge for each of the hydrographic areas, as well as to develop a distribution of the recharge, because the distribution of recharge is important for informing model development and model calibration and developing parameter estimates. And then understanding where recharge is occurring as well as where discharge is occurring can help inform the decision-making process. The vision of interbasin flow under the State Water Initiative is to identify areas and connections between hydrographic basins where interbasin flow is very important, where it's poorly constrained, where estimates are highly uncertain, and may have implications on flow systems, and then to re-estimate those interbasin flows using more direct methods rather than just depending on water budget residuals, and that will help to refine our understanding of flow systems where that is needed, and will also inform accuracy of water budgets from the other components of the State Water Initiative. And the idea here is to have the interbasin flow toolbox of methods that is much more broad than just looking at the residual of the water budget. For example, using Darcy calculations, where we look at the groundwater flow gradients and aquifer properties to make more direct estimates of the interbasin flow, using isotopic and geochemical analysis to help constrain the estimates of interbasin flow, and where it's needed to use geophysics to understand the properties or dimensions of where the interbasin flow is occurring. And so once we have new estimates of discharge and recharge and more constrained interbasin flow estimates to revise the water budgets across Nevada, and then with revised water budgets, of course, look at existing perennial yield estimates and determine if those need to be revised. And then also water budgets, of course, are extremely important for calibrating models, and which is the process of determining aquifer properties. Included in the State Water Initiative vision is the development of hydrologic models where it's needed for making informed management decisions, and in particular in river-connected flow systems where the interactions between groundwater and surface water are complex. Using the models to improve our understanding of those connections, using them to develop capture maps as well as draw down potential maps. Basically anywhere where forecast management decisions are needed throughout the state, where the information is complex and the interactions are complex. And also, of course, to help understand the potential impact to Nevada's water resources from climate change. And finally, to develop web-based application tools for interacting with the models developed under the State Water Initiative, making these tools and these applications available to all the water resource managers as well as to the public, and making all the data and reports that are collected as part of the State Water Initiative available to everyone online. On this figure to the right, we show an example of the Humboldt Capture Query Tool, which is currently under final state of development for the Humboldt study that allows users to interact with the model results to extract what the depletion rates are for any location within the basin. And then the example on the lower left is the Olson Get cloud-based tool, which is envisioned to house all of the models and allow the users to interact with those models for pre-selected output type generation and scenarios from those models. So with that, I'm going to turn this presentation back over to Adam for concluding remarks and to conclude this panel session. Thank you.
I'd like to conclude the panel presentations with a summary of the need for this initiative and some considerations going forward with regard to implementing the findings. In many cases, the baseline science that we rely upon for understanding water budgets is dated and is increasingly being challenged. We have the capability to improve this baseline science and improve our ability to make defensible and accurate decisions for long-term water resources management. The first stages of this initiative are focused on using state-of-the-art scientific methods to quantify water budget components with a consistent approach, updating estimates in previously studied areas and adding additional ones. This is the foundation that we need for future tools such as operational groundwater models to facilitate efficient water management. So what would this mean for current water users and water right appropriations? Well, improving the science in a way that might change perennial yield does not in itself have any direct effect on water rights. What it does do is help to understand the realities of long-term effects of groundwater development and water security for groundwater dependent communities and economies. It also provides a common baseline for all water resource planning at the state and local level. A key component of this initiative is public outreach and science communication. In addition to water rights administration, these data are needed to fulfill legislative directives for communities and local planning efforts statewide. County water resource plans, groundwater reserves, and a state water plan are all recent examples of legislatively directed objectives that need good foundational water budget information to be effective. The outcomes of this state water resource initiative will provide the objective and non-biased data to support these goals. If we don't take these steps now when we have the capability and the opportunity, then challenges and conflict will continue to become more difficult to resolve as water demand increases. And with that, I'll conclude the panel presentations and open it up for any questions or discussion.